All right, let's dive right into this explainer and unpack one of the most common, yet kind of fascinating, technical puzzles in electrical engineering. If you work with three-phase induction motors, you already know that changing motor conditions changes, well, pretty much everything. But today, we're going to look past the standard textbook definitions and discover the actual real-world physics behind why it happens.
Picture this. You're sitting in the hot seat of an interview, and they ask you, if we take a three-phase induction motor and run it at a significantly reduced load, what exactly is the effect on its power factor and why? Now, a lot of people know the first half of that answer, but the why, that's where it gets really interesting, and it's what separates the pros from everyone else. So let's build that answer from the ground up together.
Here is our quick roadmap for today. 1. The immediate answer. 2. Why low power factor hurts. 3. Active versus reactive power. 4. The science behind the drop. And 5. The ultimate takeaway.
Kicking things off with Section 1, the immediate answer. Let's look at what actually happens when the physical load on a motor changes.
A motor running near its full design capacity absolutely thrives. Say you have a motor and you're running it at an 80 to 85% load. It gives you a really beautiful high power factor. It's happy, operating right in its optimum sweet spot. But if you take that exact same motor and dramatically gut the load down to just 30 or 40% of its capacity, well, the power factor doesn't just dip a little, it literally plummets. It ends up running at a power factor far, far below what it was designed for.
Moving on to Section 2, why low power factor hurts. This is all about the real-world impact.
You might be wondering, hey, if the motor's job is just to produce rotation and the shaft is still spinning, why does a bad power factor even matter? Well, running a motor at a highly reduced power factor is a massive operational headache. It completely tanks your efficiency. When that efficiency drops, the internal electrical losses within the motor start to spike. And guess where those electrical losses go? Straight into heat. Your motor starts experiencing abnormal heating. Basically, it ends up working way harder, bleeding energy, and overheating just to drive a fraction of its intended load. Your overall performance just takes a huge hit.
Which brings us to Section 3, active versus reactive power. To get to the real why behind all of this, we need to unpack the physics of the two fundamentally different types of electrical power inside that motor. First up, we have active power. You can basically think of this as the muscle of the whole operation. This is the power doing the real, physical, heavy lifting. When you think about the main job of an induction motor, producing mechanical rotation to drive a load, it's the active power that is actually getting that physical work done. Second, on the flip side, we have reactive power. Now, this is the vital but completely invisible enabler. An induction motor cannot just magically turn electricity into rotation, right? It absolutely relies on a magnetic field. The sole job of reactive power is to establish that magnetic field and maintain it continuously. It doesn't turn the shaft itself, but without it, your active power has absolutely zero environment to work in. All right, Section 4, the science behind the drop. This is where we combine those definitions for the real aha moment.
Let's look at optimal conditions first. At a 75 to 80% load, the motor is doing a ton of physical work. Because of this, the active power it's drawing is huge. It still draws reactive power to maintain the magnetic field, of course, but the active power completely dominates the mix. And since power factor is essentially just a ratio looking at how much of your total power is actually doing real work, having that high active power component gives you a beautifully optimized high power factor.
But here is where it gets wild. If you drop that load down to 30 or 40%, the motor barely has to do any physical work, so the demanded active power shrinks drastically. But, and this is the absolute key to the whole puzzle, the reactive power stays exactly the same. Why? Because whether you run it at 70% load or 30% load, the motor still has to produce the exact same magnetic field just to function. So your active power drops like a rock, your reactive power doesn't budge an inch, and that crucial ratio, it just completely tanks, and that is exactly why your overall power factor drastically decreases.
Finally, Section 5, the ultimate takeaway. How do we make sure we size things right? Understanding the theory is great, but how do we apply this in the field so we don't shoot ourselves in the foot? The golden rule here is that you have to carefully analyze your load before you ever select a motor. Always, always match the motor's specific kilowatt rating to the actual demands of the application. A super common mistake is tossing in a motor with a much higher rating than necessary, thinking, oh, it's safer, it's more robust. Actually, by oversizing it, you are practically guaranteeing it will permanently operate underloaded. You're literally locking yourself into a poor power factor, terrible efficiency, and high heat losses by design.
So let's bring it back home.
Think about your own facilities for a second. If a seemingly safe, massively oversized motor is just quietly bleeding energy and slowly burning itself out over time, how many hidden energy vampires do you have running right now, just constantly draining efficiency because they're perpetually underloaded? Well, now you've got the complete picture, the symptoms, the physics, and the fix. I'm willing to bet you'll never look at a motor's nameplate quite the same way again.